Eh ben, je suis très content de t'accueillir, Alessandro, là, dans le cycle des séminaires à SystemX. C'est une occurrence mensuelle où on fait intervenir des gens sur l'ensemble de nos domaines scientifiques et techniques. Donc, déjà, c'est des chercheurs ou des enseignants-chercheurs qui présentent des travaux récents sur nos domaines scientifiques et techniques. Donc, des sujets aussi bien sur l'IA que des sujets de sûreté de fonctionnement, de cyber, des sujets ingénierie système, calcul scientifique, optimisation. Il y a donc beaucoup un champ assez large. Et bon, toi, tu as plusieurs casquettes et je vais juste un petit peu introduire ton parcours. Tu as fait une thèse à Paris-Sud il y a maintenant quelques années sur des sujets plutôt informatique, système parallèle. Et ensuite, tu as développé tes recherches dans plusieurs écosystèmes et en particulier, c'était bon de le noter, c'est que tu as fait un petit tour à SystemX. Je crois que c'était autour de 2015 de mémoire. Voilà, et donc tu as pu travailler dans le contexte du projet SCE, si je me rappelle bien. Et puis après ce passage à l'IRT, tu as été, je crois, au Brésil, où tu as été chercheur là-bas. Et puis tu es revenu en France, tu as occupé des fonctions aussi chez Safran avant de revenir à l'INRIA. Et c'est un peu pour tes derniers travaux qui nous intéressent. Enfin, tu as plusieurs types de travaux qui résonnent avec nos travaux aussi côté systémique, c'est en particulier des sujets autour de l'IA hybride, mais aussi plus récemment sur les sujets d'IA générative et de causalité. Et c'est précisément ça dont tu vas nous parler aujourd'hui. Donc, je suis très heureux de t'accueillir et puis de te laisser la parole pour donc ce séminaire sur la découverte de liens causaux dans les large language models. Je te passe la parole pour cette heure de séminaire.
Merci beaucoup, Patrick. Merci beaucoup pour l'invitation. Merci beaucoup. Donc, je vais présenter ces travaux qui étaient réalisés en plusieurs parties. Donc, ça rapporte quelle est l'utilisation des large language models dans le cadre de la découverte causale. Je pense que je vais plutôt parler en anglais, mais vous pouvez me poser les questions en français ou vous êtes libre de m'interrompre pendant la présentation. Si vous laissez, ou si vous voulez, vous pouvez faire aussi à la fin de la présentation. So, everybody knows that correlation not imply causation. For instance, here we have an example where you have the chocolate consumption of different countries around the world, and you have the number of the Nobel laureates per population. And you can see there is a clear correlation between chocolate consumption and Nobel Prize. The problem here is that, okay, I know that is indicative of Nobel Prize, but it's not, I cannot invoke a causal relationship. Why? Because if I force someone to develop policy to make everyone to eat chocolate, it did not lead to increase the number of Nobel Prize in this country. The problem is that we are not framed to think causally. For instance, if you see the floor is wet, or if I see many people use the umbrella, I associate that it's raining. Or you can also see every morning I heard the cock the hen is sing, and I say, okay, the sun is rising. So most of the time you think most causally. The problem is that if you think causally, to base on observation. And the main problem is that if you try to use the reasoning, say I rely on observation, to develop machine learning, to also rely on some observation, some abstraction of the data, of the world using the data, this can be very dangerous. For instance, here you have an example where there is a strong correlation between the grass and the land pasture and the figure of the cow. So the model is able, when there is the image match what they have seen in the past, say they are really able to give the correct class. Okay, there is give a cow, there is a correct class. But if you change a little bit, just change the background, now the model is completely blind. You can even see there is no cow anymore. Now they are only show class that are related to the background of the figure. There is the seal. And you can see here that even the class more general concepts as mammal here, where it relation to, but you can never see the call. If you try to say force the model to see what it exactly try to see, you can really show is the call or not. So you can see there is the call is not related even to the model is completely blind for the call in the figure. So there is a very little perturbation. The model can be it's not stable for little perturbation. So relying on correlation to make prediction can be very dangerous when you have distribution shift. The problem is that in many questions they are normal nature in general. For instance, you don't know what will be if I want to what will be the high. I want to hide the minimum wage. I want to say there is reduce on our poverty. I want to know, okay, if I rise the minimum wage, does reduce poverty? I don't want to only predict. I want to make some action. I need to make action in the world. I need to intervene. I don't want to know if the medicine or people on medicine will get better if I take it. I want to know if the medicine gets me better more quickly. Say, and all the time you are frame that is causal question. And if I'm in the economy, say, okay, I know that the central bank will cut the interest rate. I want to understand if there is a recession. The recession was caused by the interest rate cuts. I want to know is okay, if I know interest rate cut caused the recession. I want to know what are the causes. So for us here, the causality will be a fundamental concept that allow us to make action to support a recommendation. But most of the time, you'll be interested in asking what if question, what would happen if, or cheap counterfactual question. When you try to say, I want to answer causal question, of how will be, okay, what will be the effect of some policy, not on the estimation, as you have machine learning. And then I have the data generation. I want to know what are the law that is behind this data generated project to support some decision, so the decision makers. But everything starts by the correlation. That can be the association. The also effect there also be a strong correlation with the association, the statistical association. For instance, the chocolate consumption is still predictive of the Nobel Prize because we know there is a hidden confounder, that is the socioeconomics of the country that intervene on both. On the chocolate consumption, people have more money to buy chocolate, and there is more investment on people. There is also investment in the education, so people have this lead to Nobel Prize. It's only the problematic to rely on association that, okay, if I try to, as I said, people ask someone to create a policy to increase the chocolate consumption, they will not make the people only change that, fix the same hidden confounder, you will not increase the number of Nobel Prize. So association, not causation, that means there is a mismatch, but you need to say, okay, what exactly is this mismatch? And when you talk about causal or causation, answer causal question, what are we really talking about? What would be causal in this case? So causality is a very very hard topic to define. There is a very large discussion discuss what is causality is. But let's take a more pragmatic approach, where causality for us is something that connects the process or the cause with the effect. Where okay, if I observe the cause, if I have the effect, that means that is the cause. It's partially dependent. There is some cases, okay, if I say that X is the cause of Y, X can be the necessary cause. That means if I observe Y, that means that implies the occurrence of X. However, if I observe X, do not imply that I have Y. There is X can be sufficient or not necessary. That means that I can have some occurrence of X, not necessarily apply that all the time I have Y. And the presence of Y don't really imply that I had X before. And there is in inus conditions, there is insufficient but non-redundant parts, the more part of the epidemiology. But here, when you talk causality here in this presentation, you can think about an intervention, say an interventional approach. That means that there is a necessary insufficient condition X. I say that X is a cause of Y with respect to some variables. If there is a possible intervention on X, if I intervene on X, I change the value of X, you change in probability the value of Y. Consider that all the order of things keep constants, not change. Okay? And the existence of this intervention, that means that is sufficient to be this necessary. So X is cause of Y only if change S leads to Y in probability, keep everything constant. And normally you represent X way, that means that use the probability of Y, and given the intervention will be here, you introduce what's called an operator do, where I say do, I'm fix the value of Y, the variable Y, to small y, X, sorry. And it's different for the probability of the Y given the value of X now is X prime. For instance, if I say, okay, if I observe that is, I want to know if smoke is the cause of lung cancer, for instance. But someone say, no, there is a genetic factors that cause both people to smoke and at the same time the cancer. Now you can do now, if I fix the probability of people to not smoke and also fix the value of the genetic factor, reduce this, try to remove this is the influence. Now you'll be difference of the both probabilities will be difference. For that, let's create what's called nowadays there's the Paul-Causal hierarchy, where you have a C that is an echelon, the causal ladder, where in the first step you have we rely on only the observation, and what I observe is exactly what I take to have the decision. If I see X, we got X, low X, that means there is the value of X. That is more related to association. And when I see some value, it reinforces my belief in some other variable. X here, I put my value of Y. One example, very famous example, say, okay, there is the Kingston removal, where there is two treatment to say when we decide to remove the retreatment to apply, and you have some observation data. And the end, you have applied the treatment A and treatment B for a population, and you have observed what was the success rate of which treatment. And consider that the patient have different properties. That is the size of the stone was different. So there is small stone and large stone. And for each one, the success rate was different. So if I analyze the success rate of treatment A for the whole population, that means that it is 78%. It's less than the treatment B, that today is 83%. So if I rely on this observation, then say, okay, treatment A is better than treatment B. Now I know, okay, I know that treatment A is performed, then they remove, I know the stone removal is 78% of the B removed. Now if you compute this, take account this information, you see that the treatment A, the performs, now you'll be, if I know, okay, what will be the probability, given that I will only stratify my population now for the size of the stone, the success rate is not the same anymore, because I know that the probability of success of treatment A, given that we only use the small stone, the size is, we have a small keystone size, now I have 93%. That is higher than the same for if I apply the treatment B, on 87. And if I know that is now the treatment A apply when I have large stones, it will be lower than the population, higher than the success rate when I apply the treatment B. So despite that treatment A dominate both treatment B, both groups, the success rate small and stone, you can see a reverse when I see in the global population. That is called association reverse. That is now known in the literature as the Simpson paradox. Okay, more relaxed, say, okay, they know that treatment A is more suited by the physician, the clinician, than me, that you try to apply more frequent treatment A because it's what I only rely on observation, what I observe. But if you now climb the causal hierarchy, go now to the second level, now you say, okay, now let's work in the intervention. I not only see, but I want to intervene. I need to have what's called here the do operator. I want to fix what's happened if I fix some variable to some value, and I'll compute the success rate or the treatment for the whole population. I need to say, now it allows everyone to ask questions, like, okay, what will be the side reduce my cholesterol? What do I believe now if I have do my value, A equals some values. For instance, you can represent this information, use what's called here the causal graph. You have the size of the stone that influence both what are the type of the treatment that you choose and the outcome, the success rate. What do you want to fix? Say, I want to force. The intervention should be I force a specific value. I fix the size of the stone. I only care about when the treatment A, I say now my treatment, everyone will be assigned the treatment A. Consider that I'm applying applying the treatment A for everyone. Now I'll be able to compute what will be exact the success rate of my treatment. Consider the whole population from the small size, when they have the small stone, and the large one. This allows us to handle the simple paradox, only rely on the observation. And the last level, you have the control factor, where you say, okay, as I have intervened in the world, what would happen if everyone, for example, have applied the treatment A for all of them, something that I cannot observe, but I want to make some decision if they would have changed the way that I have to think about it. Is the contrafactor. Now you cannot observe. You return for the word, apply the model that do the intervention, and try to play if the new population have changed, something that you cannot observe. When you are in the causal inference, model interest say, if I want to answer to improbability, change A, you change it's K A is the causal B, and change A in probability change B. But sometimes the ideal case is to have the randomized control trial. And I want to be sure that what we observe and which is the value that I'm care about. And for that, randomized control trial is very simple. Everyone knows, very quick recap. You have the population, you want to split, randomly split. And for one, you give the treatment, and the other will be in the control. And you measure the difference that you observe in both population will be the result of will be the outcome of the treatment. Okay, this will be what you want to care. However, most of the time, sometimes you don't have exactly the same population. They are not have completely representative of all the population. You need to be sure that what you have in the random, the treatment and the control are the same. And the question is, okay, how can I be ensure that what you observe in one population can also be transported to another one? That can be generalized for the randomized control trial. But randomized control trial cannot apply all the time. Most of the time, it cannot even apply. It can be unethical, can be very expensive. What you want to do? Okay, I want to answer causal question, but use observation data. And sometimes this observation data was not even developed to answer this type of causal question. But I want to be as close as possible to the randomized control trial setup. Okay. So for that, you can use one of the approaches called the potential outcome framework, that you consider you have a set of individuals, a set of units. And for these individuals, you need to assign for the treatment or for the control. Where you say, okay, if I want to measure the difference for the individual that was received the treatment, and the effect will be the difference between the difference that I observed between the treatment when the individual received the treatment and when the individual was not treated, was untreated, was in the control group. However, for the same individual, you cannot observe both. treated and untreated. The individual was even it was treated or not treated. So what is called the problem of the causal inference is a problem of missing data. We cannot observe one. The other one becomes the counterfactual, the unobserved one. And if I have the population, I can also compute this. But the average effect of the whole population is on the expectation between the difference of the whole population that was treated and this individual, the population that was not treated. And you can also compute the effect, or what would be the outcome, the question I'm trying to answer, based on some covariates. That means that if I have not only the treatment that I know what the treatment that apply, but if I have other features, for instance, was the age and the status, social status, or other features, I can also include that to try to measure what would be the outcome. And for all, then you assume that the treatment is stable. That means that it's suitable. There is no hinder confound. Everyone has the same probability to be in treatment control and to really work. When you say, if I don't know what are the treatment, I might only have the observation, and I want to, based on my observation, what are the causes, the causal relationship between the variable, I want to have a framework, a causal framework based on observation data. For the first time, you start by ask the causal question, the question that you want to frame as a cause, that you want to combine the observation data and knowledge, some background knowledge. If you build a causal graph, sometimes you can also provide the causal graph. That is some part of the causal graph and try to learn from the observation data and try to identify the causes. And this cause can be IG and not IG. That means that it can be enumerated and answer the question in the end. And for that, you assume that you have observation data domain knowledge. All the variables are only moderated by the causal links. But we don't know how the relationship between the variables. This is what we want to know. We don't know exactly what are the code. Who is code? What is the cause between the variables? What are the causal relationship between the variables? Okay. For instance, imagine that we can use for that what's called a causal graph representation, where you can imagine that you have the course. There is a court, there is a captain here, there is a little C, there is a soldier, and I will say that is observe someone need to fire. And there is a prisoner if at least one of the soldiers fired. Okay. So that means use the causal representation here. You can say, okay, I have my variables, and I know that the court order will be given to the captain, and the captain now you give the order for the soldiers, and the soldier in the end you fire, and if one of them, if at least one fire, the prisoner will die. Now the way that we represent, the edge represent the causal effect, direct causal effect, and the nodes represent the variables. Based on this information, you can say, oh, I collect some data about this experiment, and I observe that the prisoner is dying. And someone can ask, okay, was the court order given? And the answer is yes, because I say, okay, if the prisoner is dead, that means that I observe one here in the end. It is highly correlated to the value of the order of the court. Okay, so the question is because it's perfectly correlated. You know that if I have the order is 1, the prisoner is died, so the probability of really die is 1. I have the same data now. The intervention. Imagine that, okay, so that A fire without the captain, there is a rebellion. Say, okay, it's fire, and the question now will be, okay, will the prisoner die? You don't have the prisoner die on observational data. The scenario is not observed, but we can use the intervention of the graph to show it. Say, okay, I know the court was not done. There was no order for the court, so the captain haven't given the order for the for the soldier to fire. However, I observe that the soldier A has fired. So if A is true, it's 1 here in this case, that means the prisoner is dying. So using these two of the causal graph enable us to ask questions that are not what's observed and do also represent our intervention. Intervention in this case will be represented by, I remove the link that was before between the part and the child here between C and A. Okay. For that, you have the causal model. For the causal model, you'll be most of the time can be represented by Bayesian network or direct causal model for us. As you know, the Bayesian network don't all the time represent the cause, do not really infer the causal representation because you can have multiple models, multiple graph representation for the same. And based on the probability, the chain rule of probability, you know that, okay, but I can compute probability given of the variable I can just do in the factorization. The probability that factorization by probability of my variable xi will be all the other variables that I have observed, I minus 1 until y1. The problem is that it's not scalable. So now we assume we can formalize that as the Markov assumption. That, okay, I know the variable will be independent probability of the variable x will be independent of all independent of improbability, all cis-dependent, all the dependents. No, it's called here the non-descendants of this variable. This allows us to say, okay, now we associate intervention in the graph with allowing probability. And for this factorization now, enable us today, okay, instead of consider all the other variables, now I'm consider only the parts of my variable that I'm trying to answer the causal question. So that means that if I observe some condition dependent in a graph, they also be I'm valid in probability. So in this case, for us, an edge will be a causal edge, direct causal between the parent and the child, and the flow will be for the parent for the child via direct paths. This is only the formalization that allows to connect the theory of the graph with the probability that was done by Gideon. So most of the time, if I say if I'm not interested in the flow from the direct cause for the other, and all the other path we try to block by create some collide, what's called the backdoor path. Let's say I don't want the path. I try to block all the paths that are not causal, that are not interested to answer the causal. Consider that we can use the graph. I have the relation now between the probability, the law in probability, and the mechanism for they represent as a graph, directed as what the manipulators call a social causal model, function causal model. Where you be the graph that I have developed before, and for each variable now you have a set of functions, and this function you'll be defining function of the parts of this variable and the noise. For each variable now it will be the noise. And this graph also imply a joint probability and assume that all the noise here, they are conditional mutually independent and also independent of all the other variables that you are observing. This will be the more that we manipulate. Okay. So our causal task, you see, okay, if I have where I try to find based on observation data, what are the causal effects between the variables, and try to understand what will be the outcome. If I make some intervention, what are the other mechanisms and in the mechanism between the function. For that, as I don't have the causal graph, I can use the causal discovery, try to, based on the observation data, try to discover what are the relationship between the variables. For instance, okay, those smokers have some data about people that smoke, or have observed people have yellow fingers, and I want to say, okay, yellow finger that is the cause of lung cancer. Let's say, no, there is only smoke that causes both. I want to discover that. And there is also causality. Okay, what will be they try to find the events that I'm unable to have another variable. You try to build this causal graph that you don't have. When you talk about the causal graph, the question is that first we start by observational data, but you need to select some algorithm that can be, there's a lot of assumptions for this algorithm to build a causal graph. Sometimes you can start for the domain knowledge, for the expert, to say, okay, as it's very hard to build a causal graph only based on the data because it's a NP hard problem, and I need to consider a very large infinite number of samples. It'd be very different to do that. That means it can help us to build this causal graph. The problem is that spec knowledge is not all the time available. And spec knowledge is also subject, can be also have some bias, also associated with some bias. This will be very shallow. Now for us, the approach to combine what's called nowadays, you can use the large language model. Say, okay, consider that large language model have a very database, a very knowledge base. You can try to help us to learn on this LLM to find what is the causal graph. And for that, we don't need to access the data, because if I need to access the data, it can be very challenging. Only give the name of the variables and some context. You give this as input to the LLM, the large language model, and the LLM, they output the causal graph. Friends here say, okay, if I want to know, I can even input the variable, some partial graph that is not oriented, and question the large language model, what would be the graph in the end? What would be relationship, friends, between smoke and life expectancy, or lung health, and also the life expectation in this case. And the LLM can run reason using his knowledge base to say, based on this knowledge, its knowledge, what will be the causal graph in the end. And for that, say, okay, I'm not saying exactly what causal LLM is talking about. Causality, one say that say it can be used to help us to find the causal graph, to build the causal graph. And the results have shown that LLM has been used for instance to find issues of the effect A and B, and you want to find, okay, A is the cause of B or B is the cause of A. And both are admissible because they are both in the Markov equivalence class. And the more that you have in the literature here, in the first section here, this part here, the algorithm, the performance is still a very shallow problem today to find a model that really able to find the true causal graph. And what was observed is that, okay, I can prompt the LLM, use different size, different type of the models, and in the beginning, say some models are at the same performance as random. It's not better than random. When the model starts to have more parameters, be more bigger, they start to have performance that nowadays can be outperform what you have observed in traditional causal discovery algorithm. And for that, can be the question is it will also depend of the type of prompt that you give, because you can give a prompt that is a two prompt per pair by variable, or I can only say, okay, given the whole context, choose what the option will be the variable. And what was shown here in this case is that this model was able to find or perform the causal discovery algorithm that based on neural networks also a very good accuracy in both of type of the prompts. So for the causal pair that is more challenging for causal discovery, what the labs say, but I can go up in the pro-cause hierarchy and check if it's also reason about counterfactual question. That means that there will be see some questions, some premise. It will be prompt about that. And in the end, the potential value, potential outcome, result of this this query. And in this case, the LLM, the large LLM was able to have a very good performance. They outperform. What is that? Because for the code counterfeit, that means that cannot observe, they need to do intervene in the world, modify the noise that you have, do some what's called the industrial step, and then say, okay, now that I have in the word that was intervened, try to answer my, see if the effect is valid or not, what would be the effect. And it was also, the model also showed that it was able to answer this type of question that is counterfactual. Okay. Nowadays, what is say, okay, but most of the people say, they are not only causal part, they only relate on common knowledge. What the people are doing today, say, instead of to try to go beyond the common sense, or that is already the vast knowledge, but that knowledge base of the LLM, people try to develop what's called the causal engine, where the LLM, they are framed to see the question, answer, derive the causal graph, and in the end, manipulate the causal graph, try to compute what is the average simple effect if the causal graph was applied or not. Okay? Try to answer all the question during the whole hierarchy of the hierarchy. What you can observe that when the LLM is able to find itself manipulate and compute what are the effects of them, the addition of the causal as the chain of thought also help the LLM to improve the performance in the whole causal hierarchy. The question here is, all of them was done, all this work all done on tabular data, was done on data set that was already had in the internet. They are available on data, they train in knowledge. And the question say, okay, what happens if the LLM also, my data is not tabular, my data is not a time series, where I have a causal model, in this case, a structural causal model, where is a time series, which time series here, and I observe these are my causal model, my structural causal model. These are how they define it. When you are working the structural causal model, you have different representation to now represent the causal graph, because I need to represent the relationship of the time of the variable over time. What is called here the full time causal graph. And not only I have one type of graph, I have now different type of causal graph represented. So by definition, that means that you have the time series, series X. I observe this in time, where my cause now will be defined in function of T observation until P, measure until P, in function of my parents, but adds and also with some noise. And you assume there is a stationary over time. For that, you can have different type of causal graph. For instance, full-time graph, they provide the whole information without inference. That can be very difficult to be inference this in practice. And you have the Windows causal graph that provide more a schematic view of the behavior. And you have the summary causal graph that only give an overview without taking account the relation, the time, it's without referring to time. And there is the standard summary causal graph that only try to say, okay, I want to distinguish between some instantaneous and like causal relation, because now the lag can be, the cause can be lag over time, can be delivery over time. Okay? And based on that, based on our work that was published, we choose to collect, to frame, to check the performance of the LLM when query about time series data, what is the knowledge to build the causal graph. And this was the time series. There was a IT system, and this was the monitor, where there is a memory middle system, where I have the consumption of RAM, the CPU, disk, and different over time, 15 seconds. And what was observed is that the LLM, and for this experiment, we did two types of experiment. First, one to give the variables the name of the variable, and ask the LLM to provide us the causal graph based on the name of the variable. Now the one to say, okay, now I'll give the time series, the plot of the time series, and also ask the prompt the LLM to give us the output, the causal graph. What we have observed is that the LLM today completely ignore the time, is only able to output the causal graph on direct a DAG without taking account the time. And the relationship between the variable, the causal effect between the variable, was only based on the common knowledge. Say, okay, I know that if they have the number of connections that I have in my system increase, I also increase the number of CPU, my CPU load, and also my run. And this run, and I know that is someone write more than the disk, but it was completely different what we have here in the true causal graph, the true time causal graph. So what we observe that it's completely unable, cannot, and very sensitive for the prompt, because if you say, okay, I know, try to force the LLM to really try to understand what I have behind the time series, it was unable. They only change the causal graph, the order of the causal graph, but without even know that is consider that they have different representation for the causal graph over time. So it's not work for time series now. Okay. Very brief, I want to say, okay, I know I have my causal graph. Someone can say, but what happens if the causal graph, I will use LLM to support me, but what happens if the causal graph is incorrect or partially correct or completely wrong? And you try to observe, okay, what if my causal graph is wrong? Consider that a very simple experiment. Imagine I have a team of doctors, and you want to say, okay, I want to decide on some patient based on the observation, what will be the severity, I observe the gender, the severity of the illness. I want to take some decision, okay, did the patient survive or not? And this was the structural causal model. And the team of the hospital want to say, okay, I want to consider that I have infinite budget, that now everyone will be treated, have the surgery, and have no budget, no one will give the theory. However, what you observe that you don't know if this causal graph is the correct one, and I don't know even if the causal graph, my structural causal graph is the correct one. It's completely unknown. And they want to build that from also rely on the causal graph. If I use the models to support us, you know that if some bias will be some problem, it will be not significant. What you use today say, based on deep generative model, many works have proposed, let's use deep generative model to try to build a structural causal model for us. The problem is that all of this work, they assume they call the structure is no. No one say, okay, I want to cast no, partial no, I don't know the partial no, I don't know exactly is correct or not. And exactly what you are interested. You're interested say, what's happened if my causal graph is not the correct one? What is happening relation to the identifiability to answer different type of question. L1 question, observation, intervention question, and counterfactual question. And for that, you assume that I have different observation. I have the observation that I have my data, and also have intervention. I do some intervention and say, okay, what will be the, I assume that I have this data. I've also collected this data, type of observation. And for that, I have developed what's called the direct constraint data augmentation, where for us, you based on the observation, my sample that I have, my called P sample of my variable, you be just the products of what I observe in my data, consider that I'm intervening in some variable, and another set of variable where I also intervene. If I don't have another type of intervention, that means I only have observation data. And then I want to see when of both of them, what would be the impact when the causal graph that I use is not the correct one. It's not output. I didn't find the correct graph, the causal graph. Okay. And for that, we try to see, okay, what would be exactly the question or the L2 identifiability, able to identify or not, when the sample that I have in my sample that I'm intervening, exactly the sample that I'm observe, consider that the causal graph are not correct, are different. what we have observed is that if the LLM or the model, the expert only know the causal order is sufficient to have a graph. There is also a subgraph of the true causal graph to really be identifiable. The question is that you will require more data, and also the test could be more complex. Okay. And for the practical point of view, for the causal discovery algorithm, say, if I want to rely on a metric, only to rely on the true positive rate, not the most important one. If I have two algorithms that have the most too close to positive rates, now you can use the true negative, but you not be very the most important one is true negative rates. Okay. We also try to find what is happening if the two classes they are equivalent, if the joint distribution are the same. We apply for that. I don't have intervention anymore. I only have the observation now. I only have the sample, and for that we rely on the separation. That means that I can have independence between the variable. And what you can interpret here in our case that I want to have the causal graph is that it's okay to have any fully causal graph. And it's safe to add more edge, for my causal graph, if they are equivalent. That means that if the class it belongs to the Markov equivalence class, it's sufficient to be fatness. That means that I'm identifiable. Okay, there's no selection bar in this case. We have tested this. You simulate on the data was the synthetic data to answer this type of question. That means what we can observe in this case, that we try to say the observation, the intervention, when there was treatment, everyone was applied treatment, no one was treated, and try to see what the effect of when you have different type of causal graph, different of graph in this variable. And what we observe is that for the equivalence class, the error is almost the same. Okay, the sum is the same for everyone, 5%. Okay, and if I'm interested, the team is interested in answer what the causal question, is only be sufficient to say, if I know is already insufficient to ask the values of the causal graph only by check. You can hear here by the capacity to recover the distribution. If I can fit the data, but cannot be enough to answer the guarantee my identifiability. We did also analyze that. We using other the state of the art that I have in this literature, different different data sets here in this case. Two data sets, one on triangle, it was the Simpson. And what you observe is that the do causal graph here, when I change the assumption of the causal graph, the performance change for both of them. They are not identifiable when I try to answer counterfactual question. That is when the causal graph is not correct. So that means that even the approach that rely on the deep generative model, deep structure causal model, they are very sensitive to the causal order. These are the details. I don't have time for that. What you can conclude for that is that relating for to say I know if my model is not really the true one, my causal graph. I want to question that. My LLM can be incomplete related to that. So what you can say that related for L1 and L2 is necessarily sufficient to consider the DAG if it is a subgraph of my two graphs. That means that I'll be able to unfalsify that. Not be able to find someone that is not valid. And from the practical point of view, true positive rate and true negative rate are the metrics to consider based on the observation data. But under the hypothesis here, there we don't have hidden confounder. Okay, there is no hidden confounder for this experiment. So, causality is really very important to make machine learning more robust for applying in the world, because we are trying to use machine learning to make prediction. Most of the time, this prediction will be translated to answer causal questions. For that, for the causal model, I need to have a causal model. The causal model rely on the causal graph. That needs to be even can be discovered using the Scalar discovery, but it's a very hard, challenging task. Now you can use okay, large language models to provide that, based to leverage on this high knowledge base knowledge that they have. And these LLM, they can outperform the benchmark that we have today in the literature for the causal discovery. This do not imply that really talk about causally, but one can be say I can really help to start a discussion about the causal graph. What we have observed is these models, they are still very sensitive to variance on the prompt. The prompt is still, they can change, okay? And they can be used as a tool to complement the causal analysis, even from the start. Cannot replace the whole causal framework. Cannot replace yet. Okay? And today they cannot handle time series, cannot answer time series question. You can ignore computer the time. And what's very important is that when I use the causal graph, I need to know what are the assumptions if my causal graph is correct, what are the guarantees that you have if part of them are incorrect. Okay, I don't know about that. And for that, there is nowadays there is the causal generative model. We have seen that they are still very sensitive to what you have for the causal order. The state-of-the-art method is still very sensitive for the causal order, for the causal knowledge. If is still an open problem, how to handle partial knowledge to build the causal graph. So this is the reference. Thank you.
Merci beaucoup, Alessandro. C'est les travaux là dont tu parles, la référence des derniers papiers, elles sont sur la slide juste d'avant là. Ok.
Ils sont tous ici, oui.
Ok. Et toi-même, tu as un papier sur le sujet? J'ai pas
Oui,
vu.
nous avons un papier. Ici, ça, c'est nos travaux.
D'accord.
C'est aussi un papier qui est en
Je
révision.
cherchais la référence. Je cherchais la référence en fait du papier.
Et il a sur archive et l'autre, il a aussi sur les.
Ok. Peut-être tu pourras
Je peux
peut-être les
t'envoyer.
rajouter. Tu pourras peut-être les rajouter en clair dans les références, comme ça
D'accord.
on pourra avoir accès directement.
OK.
Ben, merci beaucoup, Alessandro. Est-ce qu'il y a des questions dans l'assistance? N'hésitez pas, Alessandro est là, il peut répondre à vos questions. Moi, j'en avais une sur le sujet de la dynamique, parce que même si tu utilises aussi que tu as présenté les travaux sur graphe, là, euh, quand on a des relations de causalité qui sont a priori susceptibles de pouvoir changer dans le temps,
Oui.
comment on peut... Est-ce que tu as déjà travaillé sur ces cas de figure, dépendant possiblement d'autres, enfin, avec d'autres variables ou d'un contexte qui varie? Est-ce qu'on a des solutions pour essayer de pister et de traquer un peu ces relations de causalité dynamique?
La relation, quand l'enseignement dans les temps, ça veut dire qu'on considère comme si c'était une nouvelle observation. Je dis, OK, dans les temps, une fenêtre, quand on prend une fenêtre, dans cette fenêtre-là, j'observe quelle est c'est pour ça qu'on a plusieurs types de relations causales, des
Oui,
graphes, représentations
ça c'est
Windows
pour la
causal
même.
graph.
Oui, oui.
Donc, je prends une fenêtre et on va regarder qu'est-ce qu'on a dans cette fenêtre-là. Si maintenant, si dans notre fenêtre, la relation elle a changé, donc ça veut dire qu'elle est complètement indépendante de la fenêtre qu'on avait fait avant.
Oui, d'accord. C'est-à-dire que quand on a deux objets qui sont reliés par une relation de causalité, on peut imaginer que ces relations bougent dans le temps en fonction d'un contexte lui-même qui va. Donc, quand on a mémorisé avec un réseau une relation de dépendance, est-ce qu'on sait la faire varier dans le temps en fonction d'une autre variable ou en fonction d'un contexte? C'était ça plutôt ma question.
Ah, si on peut le changer, mais là, tu dis par exemple que c'est plutôt l'effet mémoire, est-ce que la mémoire courte, la mémoire longue, c'est ça ta question de sens? Ou si je peux changer, qu'est-ce que je peux le faire pour le changer? Parce que là, si je qu'est-ce que je peux changer, je vais intervenir, je vais faire l'intervention pendant, et je vais faire l'intervention et je vois quel est l'effet de mon intervention. Mais ça, j'ai besoin de fixer un temps, j'ai besoin de fixer une fenêtre. Et je vois, dans cette fenêtre-là, je dis, OK, est-ce que c'est ma intervention que j'ai observée dans cette fenêtre, est-ce que je peux aussi les voir dans les fenêtres N plus 2 ou une fenêtre dans le temps. Après, mais ça va dépendre de l'état de fenêtre ou qu'est-ce que nous sommes en train de mesurer, les phénomènes que nous sommes en train d'analyser.
Maxence, tu as une question? Allume ta caméra si tu... Comme ça, on te voit. Si elle marche. On t'entend pas, par contre. Non, on t'entend pas. Ah,
Est-ce que c'est...
ça va être
Ah, bon.
compliqué. Ah, ça y est. Là, ça y est, on t'entend.
Super.
Bonjour, Maxence.
Ok. Excusez-moi, j'ai la voix un peu cassée. J'avais une question sur un peu technique sur la façon là, dont les LLM fonctionnent là. Donc vous expliquez que c'était pas un problème d'optimisation, mais plus de la connaissance qu'ils avaient de manière générale. Est-ce que
Oui.
vous sauriez si les LLM pourraient par exemple être biaisés eux aussi par des exemples? Si on reprend des exemples comme celui du peloton de tir, est-ce que si on leur donne en entrée des tableaux comme ça avec les données, est-ce que du coup ils se trompent plus que quand ils réfléchissent plus à la question de manière générale?
Si il a, là, la question s'appelle juste que s'il fait la représentation, par exemple, il fait la représentation en termes comme des, s'il utilise seulement l'observation là, sur les données observationnelles, il va se tromper. Mais je veux dire, si on raisonne maintenant, on dit, OK, c'est pour ça qu'on fait la chaîne of thought. Si on sort des causes graves, maintenant qu'elle sort des causes graves, manipule ces causes graves, utilise comme downstream test, fait la prédiction. OK, si c'est vraiment faire le raisonnement contraire, si le prisonnier il est mort, c'était les soldats qui étaient tirés, mais ils n'avaient pas la hors des coups, il va dire OK, non, parce que seulement, c'est reste seulement sur l'observation. Mais si on lui demande qu'il manipule les causes graves, là, maintenant, si la personne qu'elle va les faire, il sera capable de dire, OK, les modèles, est mort ou pas. Si la représentation des causes graves. C'est pour ça que là, quand on parle des causal engine, là, les chain of thought, je dis, OK, c'est pas seulement sortir les graphes, mais utiliser les graphes à partir des données qui est observé et faire l'intervention. La question aussi, c'est la représentation des graphes. Si seulement, à partir seulement des données, non, on ne peut pas. Mais
Hmm.
si une fois qu'on commence à voir la représentation des graphes et manipuler les graphes, qui est la notion d'intervention, là, on peut dire, OK, si j'interviens, ça veut dire que j'ai coupé les liens qu'il y avait entre l'ordre des capitaines et par exemple, ici, les soldats. Ça veut dire qu'il a dit, OK, mais je sais qu'il a tiré et A, c'est la cause directe des D. Donc, ça veut dire que j'observe A, D est mort dans ces cas-là.
Hmm. D'accord. Et j'aurais une autre question aussi, mais là c'est peut-être plus de la curiosité. Est-ce que si par exemple on donne un énoncé au LLM d'un cas et que l'énoncé il est contre-intuitif, par exemple on lui dit le feu ça éteint pas l'eau ça éteint pas le feu mais ça l'amplifie, est-ce que ça va poser des problèmes dans sa création du graphe de causalité ou est-ce qu'il est bon à interpréter ça?
Ça va dépendre comment on va faire les prompts, oui. Mais là, parce que s'il va contre sa connaissance, sa base de connaissance, son common knowledge, son sens, qu'est-ce qu'il a, il peut dire, là il peut répondre de manière correcte. Donc, les modèles les plus gros aujourd'hui, les plus gros, comme ChatGPT, il peut déjà détecter qu'il a une incohérence dans le raisonnement et
Mhm.
sortir, dire, OK, non, non, on peut pas. C'est comme dire, OK, j'ai tiré, le prisonnier n'est pas mort. A tire, B tire, le prisonnier n'est pas mort. Il peut dire non, si on assume dès le départ que c'est A qui, si on tire ou si l'eau dans le feu, là, c'est juste dit qu'il a besoin d'avoir une intervention, ça veut dire qu'il a une source, une cause cachée, qui est
Mhm.
qui jette l'eau sur le feu, mais qui fait le feu allumé, par exemple. Mais ça va dépendre exactement de comment on va, la question a été posée. Il est encore sensible à la manière comme on pose.
Ok.
Et si on lui demande à les manipuler, sa réponse.
D'accord. Ok, bah, merci pour vos réponses.
Ici.
D'autres d'autres questions? Bien. Ben, merci beaucoup pour cette présentation et bon voilà sur des sujets vraiment d'actualité. On a d'autres sujets qui nous relient aussi autour des sujets d'IA hybride, mais on aura peut-être l'occasion d'en reparler ultérieurement. Merci
Ok,
beaucoup
avec
Alessandro
plaisir.
pour le temps que tu
Merci
as passé
beaucoup
avec
pour
nous
l'invitation.
et pour ta
Avec
présentation.
plaisir.
À bientôt.
À bientôt.